Good afternoon. Here is your video for rational versus irrational numbers. What I would like you to know is that this is a very note-intensive lesson. I encourage you to take notes on each page by hitting pause and writing down everything that you see, and then continuing on to the end where I will do more explanation. So right here, hit pause, copy all this down. Thank you. All right. So here we go. You should have copied it down. Natural numbers are the numbers that my son could count naturally. He would just start off counting his Cheerios. 1, 2, 3, 4, 5. Naturally, it's what he would count with. My son would not naturally count with 0. So when we start using 0, we now have whole numbers. Whole numbers include the 0. Once again, please hit pause, copy this down. Integers. Integers include the whole numbers that we already talked about and their opposites, the negatives. So now we've included the negatives. The whole number goes inside of the integer because anything that's a whole is also an integer. And this will make more sense at the end when I explain it further. Once again, I would like you to pause and copy this down. Rational numbers are numbers that can be written as a fraction. Any number that can be written as a fraction. If I have a fraction, I can represent that as a decimal by dividing it, and I'll either get a decimal that terminates or stops, or a decimal that repeats and goes on forever. I can also have perfect roots, square root of 25, square root of 100, and we'll have some more examples of that in a minute. So I would like, for the last one, for you to copy this down, irrational numbers. And notice that irrational is attached to the side. It's not within the section. It's off to the side of the section. Rational numbers, irrational are numbers that cannot be written as a fraction. They are numbers that go on and on and on forever as a decimal, and they do not repeat. Usually, we find these numbers from non-perfect squares and from pi. So now what I would like to do is let's just talk about a few of these different examples. And if we were in class, we would have done a few walls examples here. What I'm going to do is I'm going to copy this figure. And I'm going to bring it over, and hopefully we'll be able to better explain some of what's going on here. All right, so we have some numbers here. What I want you to know, when you think about this, and I don't have it written on here, so I am going to add it. Is that there is another box in here for the natural numbers, and those are the numbers that my son can count naturally. The natural numbers that he counts naturally are 1, 2, 3, 4, 5, so on and so forth. Then he learned part of the whole number system when he had 0, 1, 2, 3. What I want you to notice is the repetition, the repeating numbers. 1, 2, and 3 are repeated in the whole block. They were also in the natural block. That means 1, 2, and 3 are both natural and whole. They can be more than one if they fit inside the block. To be an integer, all I'm going to do is add the negatives to what I already know. All I'm adding are the negatives. So I know that I had 0, 1, 2, and 3. Now all I'm adding are the negative 3s, negative 2s, negative 1s, and they go on forever in each direction. They go forever this way, and they go forever this way. So far, I've dealt nothing with any kind of fraction or any kind of decimal. So I know that if it's a whole number, I'm going to start in one of these categories. When I get to rational numbers, that's where I'm going to add in any decimals that I see. That's how I would classify it. And I'm also going to add in any fractions that I see. If I see a fraction, I automatically am going to think rational. For decimals, it has to be a specific kind of decimal. It needs to be a repeating decimal, and I'm writing sideways, so give me a minute. Repeating. And sometimes we had confusion of what it means to repeat. Well, if I was a repeating decimal, it's like I would be 0.3333333333. Or I may even be 0.1515151515. I'm repeating. Or I'm also terminating. A lot of kids have seen the movie Terminator, and they know that terminate means to put an end to. Otherwise, maybe you just know that terminate means to extinguish, to put an end to. So I would put an end to my decimal. 1/2 is a terminating decimal, 0.5. It's done. It stops after the 10th place. It might not terminate until after the 100th place or the 1000th place, and that's okay as long as it terminates. If it does not fall into any of these categories, then it's irrational. Irrational are my non-repeating, there's not much room here, non-repeating, non-terminating, oh, sorry, I can't fit it, non-terminating decimal. Non-repeating, non-terminating decimals are irrational. One common example of a non-repeating, non-terminating decimal is pi. This decimal goes on and on and on forever, and it does not repeat. Typically, for an irrational number, it is either going to be pi or it's going to be our non-perfect square roots. Non-perfect, perfect, CT, square roots. So in my class, we were struggling with that a little bit because we forgot what our perfect square roots were. Well, remember, perfect square root of 1, perfect square root is 4, that's a 1. Perfect square root is 9, 16, 25, 36, and they go on. And most of you will recognize the pattern that this was 1 squared. That's the same as 1 squared. Same as 2 squared. Same as 3 squared. So the square root of 9 is 3. The square root of 16 is 4. The square root of 25. So on and so forth. So that 2 squared, the square root is just a 2. I don't know if the eraser will. Oh, there we go. That's kind enough. So our perfect squares then at this point are these numbers right here. These are the perfect squares. So let's start with some examples so we can kind of understand what it means to label or to find the set of these numbers. 1.9. I always start at the innermost square, just as if I was doing order of operations. I start at the innermost bracket or grouping symbol, and I would see where they go. 1.9. Does my son naturally count 0, 1, 1.9, 2? No, that would sound really funny coming out of a 4-year-old. So no, he does not count 1.9. It also is not a whole number. The fact that it has a decimal here tells me it has part of something. It didn't make it all the way to the whole mile. It didn't make it to the whole minute. It didn't make it to the whole way of whatever it was doing. It only got part of the way there. So just knowing what the word whole means, that's not a whole, that's a part. In order to be an integer, I have to be a whole number or its opposite. So it's not an integer. So now I know that I'm at a decimal, and both of these talk about decimals. Rational and irrational both talk about decimals. So I have to analyze what kind of decimal I have. Well, it stops in the 10th place. It is a terminating decimal. If it's a terminating decimal, it is rational. And that is the only classification for this number. Let's look at the next one. The next one is the square root, negative square root of 36. Well, it's up here as well, but the square root of 36 is 6, and I want the opposite of that. So I have negative 6. My son does not naturally count negatives. It is not a whole number because whole numbers only include the 0 from what I would naturally count. It is an integer though. Since it's in this integer box and the integer box is inside of the rational box, it is both an integer and rational. It has two names. It is an integer and rational. The next question, the fraction 4/5. It's not a natural number. My son does not naturally count 4/5. It's not a whole because the definition of a fraction is to be part of a whole. It's not an integer because it's not a whole. So the only thing left is rational. It is a rational number. Square root of 22. So I'm going to take the square root of 22. Let's see if it's grouped together for us. Sure is. I'm going to take the square root of 22 here. I'm going to minimize it down a little bit. And I'm going to bring it up to our other square root section. And I'm going to see where does it fit. Well, it doesn't go between 1 and 4. Not between 4 and 9. Not between here. It would fit in between the 16 and the 25. Well, 16 is a perfect square, that's a 4. 25 is a perfect square, that's a 5. So 22 is in between. 22, it's not a perfect square. So if I go over here, my not a perfect square root option is irrational. Oh, it's hiding behind. So this one, this square root of 22, is going to be irrational because it doesn't fit. Irrational. So let's think of some other examples. What are some other examples of rational and irrational numbers that we could use? And I really like this sheet right here because it makes us think of some. Definition of a whole number. I could easily say that it's my counting numbers and 0. And for my integers, I can say that it's my whole numbers, which would be all of these. It's the whole numbers and negatives. My rational numbers, I could say it's integers and fractions and decimals. And then I can even qualify my decimals as and decimals that repeat or terminate. And what do I know about my irrational numbers? Well, it matches none of these. It is all in its own. It is a non-repeating, non-terminating, decimal, or and, because usually they end up being the same thing when you find them, a non-perfect square root. Then we also have the comparison of for the circumference and the diameter of a circle, and we get the ratio of pi. So that is another example, is being pi. So then if I had to come up with a number, an example of a whole number could be 0, could be 7. An example of an integer could be 7, just like the whole, or it could be -5, to be the opposite. Example of a rational number could be 2/5, could be -3, because a rational number is still an integer or still a whole. But I could spice this up to say 3.15 repeating. An example of an irrational number could be the square root of 7. It's not a perfect square. And the square root of 38, which is also not a perfect square. There are a lot of vocabularies tied into the rational and irrational lesson, which can tend to confuse people and students. However, just take your time, use the back of the book to verify that you're doing your answers correctly. and follow the rectangle pattern that we talked about here and see if it fits in one, then it fits in all of them after it, other than this added bonus. If it doesn't fit, if it only fits in integer but not in whole, then it's integer and rational. It's everything beyond it. All right. I hope that this helps you a little bit with your homework. Remember, you're going to list them out as you go. And if you have any questions, remember to ask tomorrow when we are back in class.